All right, welcome back, everybody. Today's a special day because today we're going to be starting chapter 11. And there's just some really, really amazing mathematics that you learn in chapter 11. It's kind of like what you've been building up to for the past two courses. You kind of touch on the ideas that we're going to see at the end of chapter 11 in Calc 1 when you learn about linearizations. And I also reviewed them in the review lessons as well. But the stuff that we get in this chapter is just it's I don't know, I love it. I'll admit that I did not like it when I first learned it in Calc 2, but it became essential to my own research and just to so many different branches of mathematics. We're going to be talking about sequences and series, in particular infinite series, their convergence, and then polynomial approximations of functions, which involve these series. So let me pull up the slides because this is actually section what I call 11.0, and I should put quotations around that. This is not a section in the book, so I should even like cross this out. This is not a section in the book. This is a section that I like to incorporate before we get to chapter 11. And the reason is that chapter 11 marks the point when the type of work that you do changes drastically. So in chapter 11, most of the work that we do will involve proving things. And so you're going to have to write a lot of proofs. So I know that I encourage you to write complete sentences. I know I like say that in the syllabus, for example, and I say that in all my classes. This is now when writing complete sentences and being able to organize your thoughts in a coherent, logical way is going to be um, like critically important, critically important. But if you haven't written proofs before, if you haven't written proofs in a long time, it's good to go over some basic logic. And that's really what this section is about. This is my brief lesson in logic. There's no homework on this section. You're not going to be tested on what's in this section. For most intents and purposes, you could skip this section entirely if you feel that you were comfortable with some of the basics of logic. But I encourage you to watch this lesson anyway because it can help you a lot. You'll see why. So here's the overview. We're going to talk about just what logic is, what is validity, what is a valid argument, what is a sound argument. We're going to define what statements are, talk a bit about truth value, types of statements. I'll show you some truth tables, but we're not going to spend a lot of time talking about truth tables. Then we're going to talk about inverses, converses, and contrapositives. Those are actually very important because they are not the same thing, generally speaking. And that tends to be the thing that students struggle with when they get into the later sections of chapter 11 is the difference between a statement and its inverse or its contrapositive or its converse and so on. Then I'm going to leave you with an interesting exercise called the four card problem, which we'll talk about again in the activities. Then we're going to go over quantifiers and just basically the idea of predicate logic. Then we'll finish going over what logical fallacies are, and I'll give you just a just a handful of logical fallacies, and I'll give you the link to read up on the other types of logical fallacies. There are many, many, many of them. And then I'll leave you with some final remarks. All right. Okay, here we go. So, first of all, what is logic? So, what do we mean when we talk about logic? The definition of logic is this: it's a reasoning conducted or assessed according to strict principles of validity. Validity. So, we want our arguments to be valid. But then this kind of asks the question of what is validity anyway? What is a valid argument? So we say that an argument is valid if it takes a form that makes it impossible for the premises, the hypotheses of the argument to be true and the conclusion to still be false. So in other words, what we're saying is that if the hypotheses are true, then the conclusion must be true as well. So this basically means that through your argument, you are using quote unquote valid reasoning to get to the conclusion. And we can say that your conclusion is is true if the hypotheses are true. Now, this is different from soundness. So soundness is a bit different. An argument is sound if it is valid and the premises are true and the premises are true. So this is one of the things that I use when I happen to grade for my classes, because a lot of times students will make a valid argument, but it will not be sound. So for example, You might do a calculation. Let's say you're going to evaluate an integral, right? And you have your integral written as this nice chain of equalities, and you're doing all of the manipulations correctly, the massaging is correct, but at some point you dropped a negative, right? So at some point you dropped a negative in there, and that negative, that missing negative sign changes the result of your answer. And so what it means is that the argument you've constructed is no longer sound because there's something in there that's not true. But the process that you went through could still be a valid process, except for that small error. That means that your argument is valid, but it's not sound. So we can't rely on the result, but at least I can see that you understand how to construct the argument. And if your hypotheses were true, your argument would be sound. All right, so an argument can be valid, but not sound. And we want our arguments to be sound. So validity is a good start, but it's not the best. You need your arguments to be sound as well. Otherwise, we can't rely on them and we can't build off of them, and the truth is not preserved if you have an unsound argument. Okay, one thing you should recognize is that you've been exercising logic since birth, maybe even without realizing it. Humans are excellent at pattern recognition and we're excellent at logical deduction. We almost have this innate desire to rationalize everything. And almost, you could almost say that one of the journeys in life is wondering just how much you want to rationalize your own existence. So everyone reaches a point where they have to stop and ask themselves, how much do I want to rationalize what's going on in my life, or what existence is, or what the meaning of life is, and so on. Your brain really, really wants to do that, but it can be very tiring when you try to do that indefinitely. Um, Easy example, like how do you know not to press your hand to a hot stove? Well, at some point when you were little, somebody either told you, don't touch hot stoves because you will seriously get burnt. But more often than not, at some point you accidentally did touch a hot stove or you did touch something hot. And then from then on, you knew not to do that anymore. That's a logical deduction because you were like, oh man, if this happens, then this happens. If I touch the hot stove, then my hand will get seriously burned. I don't want my hand to get seriously burned, so I am not going to touch the hot stove. There you go. That's essentially using logic. So having a strong understanding of both formal and informal logic, it's going to help you reason better, argue better, identify fallacious arguments, and identify fallacious claims. It's a really, really important skill for any scientist, any STEM major. You have to know these skills. Once you've got a good grasp of logic, you're actually going to start to see that a lot of people behave speciously under the guise of logic, but once you start to consider their arguments or consider their claims, you'll realize that they're totally invalid or at least unsound, right? So it's good to keep an eye on this. I always say, like, don't trust anything, don't believe anything. You should demand proof, you should demand intuition, and you should demand meaning, and you should demand evidence. All of these things are required of a scientist. Okay, so be that skeptic, be that skeptic. Okay, so let's start with what is a statement. What is a statement? I have some examples and I have some non-examples. These are examples of statements. So an example, I'm 6 feet tall. That's a statement. Today is Wednesday. That's a statement. I am on Mars. That's a statement. Okay, just examples. Here are some non-examples. What time is it? That's not a statement. Uh, Quote, pizza with pineapple on it is gross. That's not a statement. Or Frozen is the best movie ever. That's not a statement. All right. So there's a distinct difference between the stuff on this side and the stuff on this side. They are not the same thing. So what is the difference between these things? What I want you to do is just kind of ponder this for a moment, philosophize for a minute, and see if you can detect the difference between these two things. Okay, and now let's get a definition. So a statement is a declarative sentence that can be assigned a truth value of true or false. So that is what defines a statement. So a statement can be given a truth value of true or false, and that's frankly it. I think maybe I'll flash forward for a minute. Let me actually flash back. Okay, so here, these types of statements, we can assign a truth value. We can say this is true or this is false, period. We could say if this is true or false, period. We could say if today is Wednesday is true or false, period. I am on Mars. We can say if that's true or false, period. This type of thing, that's not a statement because it's just a question. We can't say if that question is true or false. That doesn't make any sense. What time is it? True. Is that AM or PM, right? There's no truth value you can assign to this. Same thing with this. Pineapple, pizza with pineapple on it is gross. Is that true or false? Talk to yourself, talk to your neighbor, your parents, or whoever. Everybody has a different opinion on that, right? You can't say if it's true or false. It depends. That's not a statement. Or same thing with this one. Frozen is the best movie ever. I know that my daughter said this for many years when she was a little kid, that that Frozen is the best movie ever, and she loved it. Is that true? Maybe to her, but maybe not to me. Maybe I thought it once, and then maybe after watching it, 100 times, I was like, maybe it's not the best movie ever anymore. Um, you can't assign it a value of true or false. So that is not a statement. So that's the main thing with statements. They have to be either true or false. I'll skip the notation part for a minute, and I'll just say this. At this level, truth value is not qualitative or probabilistic. It's yes or no. So at least at this level, we're not talking about like Bayesian probability theory. We're just saying true or false. That's it. A statement is either true or false. It's not qualitative or probabilistic. So for notation, so generally when we're talking about statements and we want to look at the logic of statements, we'll use capital letters to denote statements. So for example, we might use the capital letter P to represent the statement, it is raining. That's a statement because we can say it's true or false. So when we're working with logic and we want to use just symbolic logic, oftentimes we'll let a statement be represented by a capital letter. Okay. Oh, I said that twice. That's okay. That. And I went through these examples. Yeah, this is why questions can't be statements, because you can't assign a truth value to them. All right, so here are some types of statements, and the types of statements are important, and you want to get comfortable with all the different types. There are conjunctions. Conjunctions are statements that are paired together with the word and. Maybe if you think about the etymology of the word, it'll kind of make sense. Junction basically means join or joining, and con means with. Even if you think of the Spanish word, right, it means con. So with a joining, that's and. So two statements paired together with the word and. Disjunction is is two statements paired together with the word or. With the word or. So dis meaning or in this case, not with, but one or the other, or either. So those are disjunctions. Conditional statements, and these are the ones that we use most commonly. So conditional statements are implications. They are if-then statements. So this is what a lot of theorems are. So a lot of theorems are implication statements. They're saying, hey, if these things are true, then this result is true. And those are what we're going to be using extensively in this chapter. If these conditions hold, then you get this result for free. That's what we're going to be saying. So these ones are the most important ones. Also, I'll say this. When you want to indicate an implication, we use a double-headed arrow. Do I say that on I say it later on, but the double-headed arrow, like P implies Q. So this double-headed arrow, it actually has a mathematical meaning. It means implication. It means if P, then Q. It means P implies Q. That's what that means, all right? So when you hear an implication, it means P implies Q. There's another equivalent way of expressing an implication, and that's this. This one's a bit trickier to make sense of, but it's so saying if then is the same as saying, or I should say, sorry, saying if P then Q is the same as saying this, not P or else Q. That one's a thinker, so I'm going to throw up the thinker one more time, and I want you to just ponder why these two things are equivalent. All right, moving on. So then there are also biconditional statements. So biconditional statements basically means a two-way implication. It means if and only if. So equivalently, it means P implies Q and Q implies P. So this a biconditional is a conjunction. It's saying, hey, if you've got P, you get Q, but also if you've got Q, you get P. So it's a two-way implication. It's a biconditional, right? Now, the symbol that we use to indicate biconditionals are double-headed arrows. So if you ever see a double-headed arrow, it means equivalent. It literally means equivalent. It means if P then Q and if Q then P, both together. So that's a biconditional. Definitions are actually biconditional statements. Biconditional statements. So anytime we want to define something, we define it as an equivalence. We say that these two things are equivalent, if and only this. If and only if. All right. So those are the types of statements. These are the ones you want to be comfortable with, I'll say, for the most part. And or, just remember that and means, well, we'll see in a minute. And means and or means or. Okay. All right, so let's look briefly at some truth tables. Again, this is not something that you need to be able to do or produce on a test. If you ever get a chance to take a class in symbolic logic, which I recommend every STEM major does, you'll get to play with these things in great detail, and you'll go through the entire build-up and exploration of symbolic logic. But these are what truth tables are. So we're going to let P, we're going to let P be the statement, I went to my friend's house, and Q be the statement, I went to the movies. And this truth table lets us explore the truth value of this conjunction, P and Q. So P and Q is the statement, I went to my friend's house and I went to the movies. All right? So here are all the possible combinations of true and false. So P could be true and Q could be true, or P could be true and Q could be false, or P could be false and Q could be true, or P could be false and Q could be false. And depending on those truth values, that changes the truth value of the conjunction. So let's go through this one together. If P and Q are both true, then that means that it is true that you went to your friend's house and you went to the movies. So the conjunction is true. However, if you went to your friend's house, but you did not go to the movies, then you did not go to your friend's house and go to the movies. That's false. If you did not go to your friend's house, but you did go to the movies, then it is not true that you went to your friend's house and went to the movies. That's a lie. That's a lie. If you did neither, if you didn't go to your friend's house and you didn't go to the movies, then yeah, you didn't go to your friend's house and the movies. That's also a lie, right? So here you go. This is like your parents being like, I know you're lying because I know that that's a conjunction, and no, your parents aren't thinking that. But that's a disjunction. So one thing to note about, I'm sorry, conjunction. One thing to know about these is conjunctions are only ever true if both of these pieces are true. They're false in every other situation. Now compare that to a disjunction. So a disjunction is an or statement, right? So a disjunction says, I went to my friend's house or I went to the movies. That's what that's saying. So again, same possible combos of true and false. Well, if you did both of those things, then it's true that you did one or the other or both. If you only did one of them, then it is true that you did P or Q. If you did Q but not P, it's still true that you did P or Q. The only time that a disjunction is false is when you didn't do either. So if both P and Q are false, then P or Q is false. So that's a disjunction. Now, implications. So implications are interesting. These are the ones we're going to work with the most. But we're going to change the sentences just to try to make a little bit more sense of it. Now we're going to say that P is the statement, you get above 90% in the course. And we're going to let Q be the statement, you get an A in the course. So then P implies Q is the statement, if you get above 90% in the course, then you get an A in the course. That's what this is representing. Okay, so if P and Q are true, then this implication is true. You you got above 90% in the course, you got an A in the course, that means that the implication was true. Let's say that you got above 90% in the course, but you did not get an A in the course. That means the statement was false. That means the statement was false. That was a lie. You said if you get above 90% in the course, then you get an A in the course. I got above 90%, but I didn't get an A. That means that that implication was false. I'm going to skip this line for just a minute and go down to this one. False and false. So you don't get above 90% in the course. You don't get an A in the course. That means the implication was true still. It was still true. Right. Still true. Then there's this weird one. So let's say you don't get above 90% in the course, but you do get an A in the course. In this case, the implication is still true. The implication is still true because it hasn't been invalidated. It hasn't been invalidated. So you may not have gotten above 90, you still got an A. Well, the implication was still true because the implication said, if you get above 90, then you get an A. All right, well, you got an A, but you know, like it didn't matter that you didn't get 90. It didn't matter that you didn't get 90. So in this case, it's actually still true. This is one of the reasons why you have to be very careful when you're working with logic, because if you assume something to be false, you can prove anything to be true. Yeah, you can prove anything to be true. I don't know if I mentioned that here or somewhere else, but just bear that in mind. If you assume something false to be true, you can prove anything you want to be true at that point. You can say anything you want and claim it's true. It's not going to be true, but you can argue in a valid way that it should be true. If you start by assuming something false, you can't really preserve the truth very well. Okay. Oh, there you go. There you go. I said it. I said it right here. So here's a good example. This is not my example, but it's a great example. If you want to ask me about this in class, I can give you a valid argument that proves I am the Pope after assuming something false to be true. So we'll assume something false is true, and I will prove to you that I'm the Pope. All right? Ask me about it later. This is why it's critically important not to frivolously assume that things are true. So beware out there in reality. Don't just assume things are true. Because if you assume something is true and it turns out not to be, well, you can prove whatever you want at that point. So be very, very careful. Okay, here's the truth table for biconditionals. Biconditionals are more powerful. They are only ever true when both, where is it? When both these are true. Both of those are true. So biconditionals are even tighter requirements, even tighter requirements. Okay, now let's get to inverses, converses, and contrapositives. These three concepts are really important. The reason that I say that is when students start doing proofs in this chapter, in chapter 11, they often mistakenly prove things like the converse, or they assume the converse is true, and then they show that. You have to be very, very careful about the direction of implication. P implies Q is not the same as Q implies P. Those are different. Those are very, very different. They are not equivalent, and we're going to explore that right now. So let's change the statements we're working with again, just to get some intuition. I'm going to say that P is the statement, it is raining. And I'm going to say that Q is the statement, there are clouds. So then this statement says, if it is raining, then there are clouds. And we're going to use this just to gain some intuition. So if the statement is, if it is raining, then there are clouds, then the inverse of that statement is noted this way. And the inverse basically means negate P and Q. So the inverse says, if it is not raining, then there are not clouds. And I want you to pause for just a second here and think about this. Is this a true statement? If it is not raining, then there are not clouds. Try to say something out loud. Say that out loud to yourself and see if it makes sense. All right, so hopefully you realize that that's actually not true, right? That's not true. This statement is true, intuitively speaking, right? If it's raining, then there are clouds, right? You can't have rain without clouds. So if it's raining, then there must be clouds up here. Well, this is certainly not true. If it's not raining, that doesn't mean there are clouds. You can have a clear sunny sky, right? So just because there is not rain, it doesn't mean that there are not clouds. So you got to be careful there, right? All right. In other words, these two things are not equivalent. They are not saying the same thing, and you got to be careful. Okay. What is the converse? So the converse is where you reverse the order of things. So the converse is Q implies P. All right. So the converse is if there are clouds, then it is raining. So think about that. Is that one true? If there are clouds, then it's raining. What do you think? Okay, say something out loud. What do you think? Is that a true statement? All right, let's talk about it. So that's not true, right? If there are clouds, then it is raining. That's definitely not true because there are lots of times where there are clouds, but there's no rain. So it's not true that if there are clouds, then it's raining. And what that's telling us is that when I say something like, if it's raining, then there are clouds, I'm not saying the same thing as if there are clouds, then it is raining. The direction of the implication is critically important. These are not the same statement. So be careful when you go to prove things that you're following the direction of the implication correctly, because it won't be true if you go backward. They're not the same thing. Okay, now here's the interesting one. Contrapositive. So a contrapositive is when you negate both statements and you switch the order. So you negate and switch. So the contrapositive of this statement is if there are not clouds, then it is not raining. So think about that one for a minute and let me know if you think it's true. Hmm. If there are not clouds, then it's not raining. All right, call it. What do you think? Is that true or false? All right. Okay, what do you think? That one is true. That one is true. That's right. So I'm hoping that you said it was true. If there are not clouds, then it is not raining, right? We need clouds for there to be rain to begin with. So if there are no clouds, then there's no rain. All right. So this one is interesting because I say it on the next slide, but a statement's contrapositive is actually equivalent it's equivalent. A statement's contrapositive is equivalent to the statement in truth value. The truth value is preserved, all right? So these I've said a bunch of times. The direction of implication is important. This is what I just said a second ago. A statement is equivalent to its contrapositive. So if you negate and switch, you have an equivalent statement, all right? But if you just switch, you don't have an equivalent statement. And that's what I'm saying right here. A statement is not equivalent to its converse. So just because P implies Q, it does not mean Q implies P. Not at all, no sirree. No, no, no. But a statement is equivalent to its contrapositive. So P implies Q is the same as saying not Q implies not P. All right? So, good thing to keep in mind. These ideas are really, really, really important to wrap your head around. That's why I wanted to like add this stuff in here before we get into a lot of theory and like learning theorems and stuff in chapter 11. Okay, so now here's the four card problem. This is a good way to test your understanding of these different types of statements or inverses, converses, and contrapositives. So here's the experiment. You are shown one side of four cards and you were told that each card has a number on one side and a letter on the other side. You are told if a card has a vowel on one side, then it has an even number on the other side. You want to know whether this is true or false. So the question that I'm asking is, which of the cards below do you need to turn over to test the claim, and why? All right, which of those cards do you need to flip over to test the claim, and why? All right, so think about this for a minute. All right, now say something out loud. Which cards do you think that you need to test? And better yet, you should call your group member or call a friend and see if they can help you figure this out and see what answer they give. All right? So say something out loud. All right, okay. Now, what is the answer? We will talk about that in activity. Other than that, I'll leave it for you to think about. But think about it and we'll talk about it when we meet in person. All right? Okay, so moving on to predicate logic. So we've been talking about sentential logic. Now we're going to talk a bit about predicate logic because a lot of times we want to quantify a statement and their truth value based on that quantification. So this is what's called predicate logic or quantifier logic. In other words, there are quantifiers involved that change the truth value of the statement. So in particular, there's two quantifiers. There's the universal quantifier and the existential quantifier, and that's what we're going to talk about here. So the universal quantifier is denoted by an upside down capital A, which is pretty cute. And the universal quantifier is used when you want to say that when you want to say that all elements of a set have some property. So these are the statements that have the words for all, or for every, or for each, or for any in them. So a lot of times people will say like, oh, this is true for all of these, or for all of these things, it's true, or for every this is true, or for each one of these, this is true. That's a universally quantified statement. You're saying it's true for all. Here's an example down here. So for any natural number n, 2 times n is an even number. Okay, so the quantification here is for any. We're saying for all possible integers, 2 times that integer is an even number. That's a universal statement. It's a for all statement. All right. Notice here I actually indexed the statement by n because it depends on n. It depends on n. So that's the universal quantifier. The other one is the existential quantifier, and that's denoted with this backwards capital E, which is another really cute symbol. So the existential quantifier is used when you want to assert that at least one element has some property. So it means there exists. So colloquially, these are statements that say there exists some number such that blah, 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 or for something, blah, 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 blah. So it's kind of at the opposite end of the spectrum as the universal quantifier. It's basically saying there is at least one where this is true. There exists at least one where this is true. That's what that's saying. That's the existential quantifier. Check out this example. So this example says sine of theta equals 1.3 for some angle theta in the interval 0 to 2 pi. Wait a second here. This is saying for some theta. So this statement says there exists an angle in this interval where sine of that angle is 1.3. In this case, that statement is false, right? That's false. There is no angle in this interval for which sine of that angle is 1.3. In fact, there isn't any angle for which sine of that angle is 1.3 because sine is bounded between -1 and 1, right? So just because we have a quantification doesn't mean the statement is true, right? This statement actually is true for any natural number n. Oh, sorry, this is natural numbers, not integers. For any natural number n, 2 times n is an even number. That is true. That's true for all natural numbers. This one turns out not to be true for any. This is not true for any angle theta. All right, so those are the difference between universal and existential quantifiers, and they are not the same thing. Very much not the same thing. All right. All right, so here's some questions related to validity. And these ones, I want you to kind of think about, let me see here. Let me see here. I might do one or two of these, but I'll leave the rest for you to think about, and we can always talk about them more during the activity time, all right? But let me start with the first one. Are these arguments valid or not? The first one says, if you work hard, or sorry, if you don't work hard, then you won't succeed. You worked hard, therefore you will succeed. Is that a valid argument? What do you think? What do you think? All right, say something out loud. Call it. What do you think? Is that a valid argument or not? All right, the answer to this one is no. This is not a valid argument. So look at this statement. This statement says, if you don't work hard, then you will not succeed. But then here you're just saying that you did work hard, therefore you will succeed. No, that's not actually, that's not what this statement is saying. So this argument is not valid. This statement is saying if you don't work hard, then you won't succeed. It doesn't tell you what happens if you do work hard, only what happens if you don't work hard. So if you think about it like this statement right here, this is like saying not P implies not, oops, implies not Q. Here you're saying P, therefore Q. That's not a valid argument because a statement is not equivalent to its inverse. This is just the inverse of that statement. It's just negating the parts, right? Those two things are not equivalent, so you don't get that result from that. That's the idea. All right, let me do, let's see. Oh, let me do this one. I'll skip the second one. We'll do this one here, and then I'll leave the other two for you. In particular, I want to leave this one for you all to try on your own, and we can talk about it later. Let's do this one, though, because it's got a quantifier. So this says, all comedians are funny. Shelley is not funny. Therefore, Shelley is not a comedian. Is that a valid argument? Think about it for a minute. And say it out loud. With a lot of these things, a lot of these statements, you got to say them out loud many, many times to make sense of them. So try it yourself. Try to say it out loud. All right, now let's work on this one together. So the statement in the beginning is that all comedians are funny. All right, all comedians are funny. So in other words, if you are a comedian, then you are funny. Now, regardless of whether we believe that's true or not, the point is this statement is saying if you're a comedian, then you are funny. Shelley is not funny. Therefore, Shelley is not a comedian. This argument is valid. This argument is valid because this is the contrapositive of this statement. That's essentially what it is. So let me write it out using the symbols. All comedians are funny. This is saying if you're a comedian, then you're funny. This is saying Shelley is not funny. Therefore, Shelley is not a comedian. That's correct. That's a valid argument because a statement is equivalent to its contrapositive. So that is a valid argument. So if you know something is true for all things in a set, and you know that that thing does not have that property, then that thing can't be in that set. That's the idea. Okay, I leave the other two for you to practice and ponder. I encourage you to talk to your group mates about it, and we can talk about it in the activity session. But let's move on to logical fallacies a little bit and then try to wrap things up. So what is a logical fallacy? A logical fallacy is just a mistaken belief, especially one based on an unsound argument. These things happen a lot. So a fallacy is a mistaken belief, usually based on an unsound argument. All right. Um, Everyone falls victim to logical fallacies. So let me just say that outright. So don't feel too bad. Everyone falls victim to these things. Everybody uses them on accident, sometimes on purpose. They're all over the place. The true crime occurs when they're used as support for an argument, because then you really can't. Oh no, one of my AirPods just died. Okay, I got to wrap this up. Um, uh, yeah, you can't preserve the truth when this is going on. They're very common in everyday discussion. Oh, wait a minute. Wait, test. Okay, hold on. Let me check this out. Okay, I think I have one more bit left. Okay, I'm going to keep going. Um, Logical fallacies are very common in everyday discussion, especially internet forums, on the news, and especially politics. However, they are forbidden in science and math. Yay! So when you're doing science and you're doing math, we are not allowed to use logical fallacies of any kind. of any kind whatsoever. They are forbidden. Now, knowing about these fallacies, being able to recognize them will help you think rationally, and it'll help you detect lies. It'll help you know when something is false or when somebody is trying to lie to you, all right? So these are important things to know. Big idea is no logical fallacies. Logical fallacies are not allowed. No, 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 no. Try to protect yourself. I'm going to give you a list of some of them, but not all of them by any means. If you would like to read a I don't know if I'd say complete list, but a long list, you can follow this link here and see all the different types of logical fallacies. So I'm going to read a few of them and talk about them, and then we'll call it a day. So here's a big one. So this is called the fallacy of composition, and that's saying that assuming that something true, something that's true for part of a whole must be true for the whole itself. That is not a valid argument. That is a logical fallacy. Just because something is true for part does not mean it's true for the whole. And a good example of this is using an example as a universal proof. So let's say you show that something is true for the number 2, and then you claim that it must be true for every even number. That's not correct. That's not correct. Just because you showed that it was true for one even number, that does not mean it's true for all even numbers. That's not true, right? So that's a fallacy. This one's called the false dilemma or the false dichotomy. This is saying this is when two alternative statements are given as the only possible two options, when in reality there are more. There are more. That's called a false dichotomy. You're saying that there's only two possibilities, but in reality there could be many, many possibilities. That's called a false dichotomy. Here's false equivalence. This is when you're describing two or more statements as virtually equal when they are not, when they are not equal. All right? So that's a false equivalence. Anecdotal fallacy. Sometimes you have a tendency to want to use personal experience or an isolated example instead of sound reasoning or compelling evidence. It'll be like, oh, well, I felt that way, or that's what I went through, therefore it must be true in general. That's actually a logical fallacy. That's not a valid argument. Um, Personal experience and personal anecdotes can inform you, can give you some intuition about what to expect, but they are not a proof. They are not a proof, and we cannot build science off of that. All right. Appeal to probability is another common one. It's likely to happen, therefore it will happen, right? There's a really, really good chance that I can win, therefore it means I'm gonna win. No, I'm sorry. That's not true. That's a fallacy. Fallacy of the single cause. Frankly, the fallacy of the single cause is saying that there's only one thing that is causing this, when in reality there could be many, many things that are causing this. That's the fallacy of the single clause. Hedging. Hedging is a popular trick to use on people. It's very, very frustrating and aggravating. Hedging is when you refine a claim in the face of counter evidence, and when you assert that the refinement was the original claim. It's kind of like making an argument and then somebody proves you wrong, but then you're like, oh, well, when I said that word, I meant this other thing when I used that word. That's what I meant. You just didn't understand that that's what I really meant when I used that word. That's called hedging. That's called hedging. It's basically getting proved wrong, but then you're like, oh wait, I actually meant this when I said that word, and then you're like, yeah, that's what I actually meant. Yeah, that's fallacious argumentation. That's a logical fallacy. Another thing to keep in mind when you're proving anything is what's called onus probandi. The burden of proof is on the person who makes the claim, not on the person who denies or questions the claim. So if you want to claim that something is true, or you want to say that something must be a fact, it is up to you to prove that fact. It is not up to the rest of the world to prove that that's not a fact. Okay, so onus probandi, the burden of proof is on the person who makes the claim. All right, keep that in mind. Proof by verbosity. So now it gets kind of funny. A proof by verbosity is basically making an argument that is so complex or so verbose that nobody can reasonably deal with it and all the intimate details. So a lot of times you'll find that when somebody's trying to claim something is true, they'll just keep talking and 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 talking at you, giving you 1,000 details in the span of like a minute, and they'll be like, haha, therefore I'm right. No, no, that's not how it goes. Yeah, you have to explain your argument in a clear, precise, unambiguous way if you want to claim truth. Yes, clear and so throwing a billion words at me does not count as a proof. That's what that means. Moving the goalposts or raising the bar. I'm sure all of you have heard this one before. Moving the goalposts is when an argument in which evidence is presented in response to a specific claim is dismissed, and then some other, often greater evidence is demanded. So it's when you're trying to prove something and you provide evidence to support that, but then somebody denies that evidence and says you need more, and keeps doing that and keeps doing that and keeps doing that. That's called moving the goalposts. That's a fallacious technique. It's not a valid technique of argumentation. Here's a couple classic ones. Post hoc ergo propter hoc. Simply after this, therefore because of this. It's very common to think that because something happened after an event, that it was caused by that event. But that's a fallacious argument. That's not always true. So you cannot just rely on the fact that because something happened afterward, it must have been caused by the thing before. Similarly, there's this one, cum hoc ergo propter hoc. This means with this, therefore because of this. So in other words, correlation implies causation. Or in other words, that two things happened at the same time or with each other, therefore they're related in some way. No, that's fallacious argumentation. Yeah, that's not a valid argument. Just because two things happened in the same time as each other doesn't mean that they're connected. Okay. All right, so I'll leave it pretty much at that. The last little bit I'll tell you about is red herrings. So a red herring is an argument given in response to another argument, which is totally irrelevant and draws attention away from the subject of the original argument. This is basically throwing out totally unrelated things and trying to distract somebody from the original argument. Examples, there are a lot. There are a lot. So I won't go into the examples, but you can see lots of them on that page that I linked earlier. If you go to this, you can read about all the different red herrings, okay? But I won't go into all that. All right, now just some closing remarks. Just want to re-emphasize that understanding formal and informal logic is imperative for clear and rational thought. You're not allowed to use logical fallacies at any point in an argument. And if you use a logical fallacy at any point in an argument, it invalidates your argument. The truth is lost. We can no longer use what you have said to build anything. So the truth is lost. And I'll reiterate this. The direction of implication is critically important since a statement is not equivalent to its converse. You really have to think about, what am I assuming and what do I get as a conclusion? All right, follow the direction of implication. Universal versus existential quantifiers have to be considered. Just because you prove something true for one item does not mean that it's true for all items. All right, and then lastly, always consider the logic in what you do and what you think. Ask yourself why, ask yourself how, and ask yourself what. All right. Okay, so that's my whole spiel about logic. I'm willing to talk more about it later if you're interested. Again, this is not a logic class, so we can't really dwell on these ideas for too long, but I hope that you talk to your group members about these things. And I honestly encourage you to take a class in symbolic logic. So if any of you are going for a STEM degree, which I'm hoping many of you are, take a class in symbolic logic. It's actually a philosophy class. So it's usually taught by the philosophy department, but it's very, very mathematical, and it'll teach you a lot about how to really, really rigorously reason about things. All right, I loved it when I took it. All right, that's it for today, and I will see you all next time.